A basic oscilloscope consists of three different systems: the vertical system, horizontal system, and trigger system. Each system contributes to the oscilloscope's ability to accurately reconstruct a signal. When using an oscilloscope, you adjust these settings in these areas to accommodate and capture an incoming signal. Today, we will discuss how to properly adjust your vertical and horizontal scale when setting up your oscilloscope. Let's get to it. Before we talk about the vertical and horizontal control systems, I first want to mention the AutoSet feature. This is a tool that can be very helpful when first trying to display your signal. AutoSet is a feature that automatically analyzes the waveform's characteristics and adjusts the oscilloscope's acquisition, horizontal, trigger, and vertical scale settings to typically try to display 4 to 5 waveforms of the signal. AutoSet should be used when you want to quickly view a signal with an unknown frequency and level characteristics. I would recommend using AutoSet to give you a good overview of your signal of interest. Then simply adjust the system controls manually to bring the signal into the view that you need. Let's do a quick demonstration on how to use the AutoSet feature on your oscilloscope. For this demonstration, I will be using a TBS 2000B, and I have a 10 times attenuation passive probe connected to the probe compensation pin. The probe compensation pin should output a 5-volt 1 kHz square waveform. First, let's push the default setup button in the resource section of the front panel. This will set the scope to its default state, 1 volt per division vertically and 4 microseconds per division horizontally. Now press AutoSet at the top of the front panel to automatically scale and display the signal. As you can see, the 5 volt peak-to-peak 1 kHz square waveform from the probe compensation output port is now displayed on the screen with 5 cycles. Once you have a good view of your signal, now you can start to adjust the vertical and horizontal controls. The vertical system controls are used to position and scale the waveform vertically, set input coupling, and adjust other signal conditioning. Common vertical controls include position. The vertical position control allows you to move the waveform up and down so that it's exactly where you want it placed on the screen. Coupling. Coupling refers to the method used to connect an electrical signal from one circuit to another. The coupling can be set to either DC or AC. DC coupling shows all components of an input signal, while AC coupling blocks the DC component of a signal so that you only see the waveform centered around 0 volts. And bandwidth. Most oscilloscopes have a circuit that limits the bandwidth of the oscilloscope. By limiting the bandwidth, you can reduce unwanted noise that appears on the displayed waveform, resulting in a cleaner signal display. It should be noted that while limiting noise, the bandwidth limit can also reduce or eliminate high-frequency signals and content. Properly understanding and setting your vertical scale is important to ensure that you are getting the best signal resolution and minimizing quantization error. Signal resolution is basically the smallest quantization level that can be determined by an analog to digital converter in the oscilloscope. The more the number of bits an ADC has, the better the vertical resolution the oscilloscope has. As an example, the TBS 2000B has an 8-bit ADC that can encode an analog input to 1 in 256 different levels, since 2 to the 8th equals 256. It should be noted that the top and bottom 3 quantization levels are typically reserved to indicate and detect signal clipping. To get the best signal resolution, use the most sensitive vertical scaling setting while keeping the full waveform on the display. If the waveform is scaled to consume almost the full vertical display, then you are making full use of your oscilloscope's ADC. The vertical settings control the Y or amplitude axis. Now let's talk about the X or time axis. The horizontal controls are used to scale and position the time axis of the oscilloscope display. There is a dedicated front panel control for setting the horizontal scale in time per division of the display, and another setting for the horizontal position of the displayed signals. The horizontal scale sets the time scale in seconds per division and automatically adjusts the sampling rate for all waveforms. This makes the waveform appear wider or narrower on the display. The horizontal scale also sets the time window displayed on the oscilloscope. Since the TBS 2000B has 15 divisions horizontally, the time window is equal to horizontal scale factor times 15 divisions. Horizontal position shifts all the waveforms on the display left or right. The horizontal position is aligned to the trigger position. Shifting the position or trigger marker to the left allows for more post-trigger data, and shifting the trigger marker to the right allows for more pre-trigger data. Pre-trigger data shows details that occurred before the event of interest, and post-trigger data shows what happened after the event of interest. For a digital oscilloscope, the horizontal scale settings are easy to use, but when you change the horizontal scale on a digital scope, a lot goes on. The scope changes not only the time scale, but also the rate at which it samples the input signal. It is important to understand the sample rate and record length to accurately reconstruct your signal. Digital oscilloscopes sample the input signal at a frequency called the sample rate, measured in samples per second. To properly reconstruct these signals, the Nyquist sampling theorem requires that a sample rate be at least twice the highest frequency being measured. That's the theoretical minimum, though. In practice, sampling at least 5 times as fast is generally desired. Digital oscilloscopes capture a specific number of samples or data points, known as the record length for each acquired waveform. The record length divided by the sample rate specifies the total time in seconds that is acquired by the oscilloscope. It should also be noted that if you increase the horizontal timescale to 40 milliseconds per division or slower, the scope will be placed in roll mode. Roll mode is typically used when viewing a low frequency periodic signal. In roll mode, the trace moves from right to left along the x-axis. The time base remains static and the waveform moves, rather than moving in response to triggering as in a conventional mode. With all the information that we have just covered, I hope you now have a better understanding of your scope's vertical and horizontal control systems. You should now be able to set up and view a waveform using your TBS 1000Z or TBS 2000B.